Hi, welcome back to the first tutorial of today, which is about generalization and representational geometry. So the connection that we mentioned in the introductory lecture about the generalization from one stimulus to another is a notion of similarity, which gives one of the justifications for comparing representations based on their similarity structure, and also connects this day back to the rest of the Neuro AI course, where a lot of the lectures are about generalization. So let's look at what you'll be doing in this tutorial. The general idea is that we'll be looking at the linear readout model. So the idea is that you have some x, which is a representation in some deep neural network, and we will be fitting a linear function from this representation to some readout that we are interested in. So similar how we would do fine-tuning for a deep neural network. And all we need to fit here is just some weights for the features that recombine the different features into the prediction that we want. Nicely enough, the parameters that we need to make optimal prediction are analytic for this. So this is just the result that you get for beta to predict y as well as possible in the least square cent with some rich regularization. Now, for generalization, we are of course interested in the question, what happens if we change some of the y's in our training data? How does this affect predictions? So we'll get one step further and just write down the equation for what will our predictions be at some test stimuli, xp, which we then multiply with our beta estimate, so with the equation on top. And what we see then is that, first of all, this is a linear equation, right? So if we change something in y, we'll get a linear map of that as a change in our predictions. And furthermore, we notice that this whole thing here is a positive definite matrix, such that this whole equation becomes a scalar product between the representations for which we want to make the predictions and our training data. So the weight for how strongly a change in our training data affects our predictions is a measure of similarity between the training stimuli and the test stimuli in the representation. And to make this more intuitive to you, you'll be applying this to an MNIST example. So to some actual networks that were trained on MNIST, which is this database of just handwritten digits. And the whole task of those networks is just to output which of those digits it was. And for this one, you can then actually generate this kernel, right? So this is the similarity between this 5 and this 7. This is the similarity of this 5 with this 2. And, down here is the similarity of this 9 and this 1. And what you should be able to see is that if you change the training data, which are just those few digits, you'll see changes down here in the predictions that are just proportional to how big those values in this matrix are. So you should be able to experience that indeed these changes correspond directly to similarity. And in this case, we coded everything such this is actually running the linear regression in the background, so there is no cheating or presupposing that the things I derive are actually true. And with that, I hope you'll have fun exploring this tutorial and learning that generalization is indeed strongly related to similarity. See you later.